It seems like everywhere you turn these days, it's all about the need for more fresh water, right?
Yeah.
And at the same time, we need all these materials to build a greener future. It's like we're
Right.
constantly trying to squeeze out every last drop and dig up every single resource we can find.
Yeah, for sure.
Then you've got something like desalination,
Right.
which is fantastic for getting us more water, obviously. But then it leaves behind this super salty brine, and then we're stuck with this problem of what to do with it. It's kind of like a headache, isn't it?
It is, yeah.
Yeah.
It's definitely a challenge. And as desalination becomes more and more common, especially with all the water scarcity issues we're seeing, the sheer volume of brine being produced globally, that's becoming a big worry, a real environmental concern.
Right.
I mean, we're talking about potential damage to marine ecosystems if it's just dumped back into the ocean.
Exactly. It's like we solve one problem and create another one.
Yeah, exactly.
But here's the thing. What if, instead of being this problem, this brine could actually be a source of something valuable?
Oh, that's interesting.
That's exactly what we're going to look at in this deep dive.
Okay.
We're going to be looking at a paper called Material Extraction Potential of Desalination Brines.
Yeah.
A technical and economic evaluation of brines as a possible new material source.
Okay, so looking at brine as a resource.
Yeah, turning waste into something useful.
Be interesting.
What do you think?
Yeah, I mean, that's a really exciting prospect. And this paper really dives into this idea
Yeah.
that desalination brine, it's not just something to be disposed of.
Right.
It could be a reservoir
Yeah.
of all these important materials,
Yeah.
especially the materials that we need more and more of for technologies,
Right.
renewable energy, electric vehicles, all that kind of stuff.
To really get to the bottom of this, the researchers, they didn't just look at one thing.
Right.
They considered how much more fresh water we're going to need in the future, what's actually in seawater, you know what I mean?
Yeah.
Across the globe, and even how we could pull those valuable materials out of the brine.
So they looked at the whole process
Yeah.
from start to finish.
Yeah. It's very thorough.
So in this deep dive, our mission, should we choose to accept it, is to figure out how much of this stuff could we actually get by 2050,
Okay. Makes sense.
And also, what are the challenges?
Right, the practicalities.
Yeah, the technical and economic hurdles we'd have to overcome to actually make this happen.
Yeah, that's key. Because potential is one thing, but making it work in the real world is another.
Exactly. Let's set the stage first. The paper starts by laying out some big global trends. To tackle climate change, we're all trying to move away from fossil fuels.
Yeah, decarbonization, net zero, it's all over the news.
They call it defossilization in the paper.
Right.
And this whole transition, it depends on a huge increase in renewable energy technologies.
For sure.
Like we need way more wind farms, solar panels everywhere, and then we'll need batteries to store all that energy and power our electric cars.
Yeah, the whole system has to change.
The numbers are pretty wild.
Oh, yeah.
The paper talks about an 11-fold increase in wind power.
And solar capacity potentially hitting 70,000 gigawatts.
70,000. That's enormous.
Yeah, it's hard to even imagine that much solar power.
It's a lot of panels.
And then they're saying that electric vehicle sales could reach 70% of the market, or even more.
So a majority of new cars would be electric.
Pretty much, yeah.
That's a big shift.
And this is where it gets really interesting for our conversation about brine.
Okay, why is that?
All this green tech, all these wind turbines and solar panels and batteries, they all require a lot of raw materials to make.
Of course, they're not made out of thin air. We need raw materials for everything.
Exactly. And the problem is some of these essential materials, we just don't produce that much of them right now.
Okay.
And the known natural reserves are limited. So this raises concerns about supply bottlenecks.
That makes sense. If the demand suddenly skyrockets, but the supply can't keep up, you're going to have problems.
Exactly. It could actually slow down the transition to sustainable energy.
So it's not just about building the tech, it's about having the materials to build it with.
That's it. The paper lists a bunch of these potentially tricky elements. Chromium, cobalt, copper, lithium, manganese, nickel, silver, tellurium, and even those rare earth elements like neodymium and dysprosium. It's a long list.
Yeah, it sounds like the periodic table of elements we need to worry about.
Pretty much, and we've got to make sure we have access to all of it.
That's a big task.
At the same time, we're facing more and more pressure on our freshwater resources. Population growth, agriculture, climate change, it's all contributing to water scarcity.
Yeah, absolutely. Water stress is a growing problem around the world.
And that's where desalination comes in.
Right, because we need that fresh water.
The cost of solar and wind energy has come down so much that it makes desalination much more viable.
Makes sense. If you can power your desalination plants with cheap renewable energy, that's a big plus.
Especially in regions where water is really scarce.
So it's a potential solution, but as we said before, it comes with the brine problem.
Right, and as you explained earlier, desalination leaves behind this concentrated brine.
Yeah, because you're essentially removing the fresh water, leaving the salts and other stuff behind.
And if a plant recovers 50% of the water as fresh water, the brine is twice as salty as seawater.
Exactly, it's concentrated. And by the way, when we talk about desalination, we often mean SWRO, seawater reverse osmosis, which is a common method.
SWRO, got it.
Just so we're on the same page.
So dumping this super salty brine back into the ocean can really mess things up for marine ecosystems.
Right. It disrupts the natural balance.
So here's the potential win-win.
Yeah.
What if we took that brine and extracted the valuable stuff in it? We could deal with the environmental problem and get important resources.
That's the idea, turning a negative into a positive.
We already get some things from seawater, like sodium, potassium, magnesium, and calcium.
Yeah, those are already commercially extracted?
But this paper looks at going further,
Okay, what do you mean?
getting other elements that are often less concentrated, and maybe even aiming for zero brine discharge.
So removing everything of value before any brine is disposed of.
Yeah, that's the ultimate goal.
Ambitious, but interesting.
The paper makes this point. The total amount of materials in the oceans is huge.
Way more than what we find on land, right?
Exactly. But many of these elements are present in tiny amounts, making them difficult and energy-intensive to extract.
That's the challenge, the economics of it all.
But with renewable energy becoming cheaper and more desalination plants being built, the situation could change.
Right, because those are two big factors. If energy is cheap and you have a lot of brine, it becomes more feasible.
Especially if the materials are valuable enough.
Exactly. The value has to justify the effort.
Now, to get into the specifics, the study focused on two elements, lithium and magnesium.
Okay, why those two?
They're a good comparison. Magnesium is relatively abundant in seawater.
So potentially easier to extract.
Lithium is much less concentrated.
So more of a challenge.
They wanted to see the range of possibilities and difficulties.
Makes sense. It's like a test case for different types of elements.
Both of these elements are pretty crucial these days. The paper calls magnesium a critical raw material.
Why is that?
Well, China currently dominates magnesium production.
Oh, so there are concerns about supply security.
Exactly. And magnesium is important for wind turbines and electric vehicles.
Yeah, I can see why it's considered critical.
And then you've got lithium, the battery metal.
Everyone's talking about lithium these days.
It's essential for batteries, from smartphones to electric cars and grid-scale energy storage.
Yeah, the demand's only going up.
The paper mentions that we currently get most of our lithium from Salt Lake brines.
Right, those are known sources of lithium.
But there's a key factor in extracting it. The ratio of magnesium to lithium.
Okay, how does that affect things?
If there's too much magnesium compared to lithium, more than 8-to-1, it becomes much harder and more expensive to separate them.
So the ratio matters a lot.
And here's the problem with seawater and desalination brines. The magnesium to lithium ratio is about 7,000 to 1.
Wow, that's a huge difference.
So the already low concentration of lithium is even more challenging to extract.
Because it's mixed with so much magnesium.
Exactly. So how do we tackle this lithium extraction problem? The paper outlines a few potential paths.
Okay, let's hear them.
Some are simpler in theory, like solar evaporation.
Just let the water evaporate naturally.
Yeah, but it would require vast areas of land and take a very long time.
Not very practical, especially on a large scale.
Right. Others involve more complex technologies like electrodialysis, membrane technology, adsorption, and desorption.
Those sound more high-tech.
They are, but many are still being developed or need to be improved for desalination brine.
Because the brine has a complex mix of different ions, right?
Exactly. But this study focuses on one particular method, Path 3.
Okay, what's path 3?
It's an electrochemical approach using these things called lambda MnO2 ADG electrodes.
Wow, that's a mouthful. Can you explain how that works?
Sure, it's a two-step process.
Okay.
The first step is using the lambda MnO2 electrode to attract and capture lithium ions from the brine.
So it's like a selective filter.
Yeah, you could think of it that way. At the same time, the silver electrode reacts with chloride ions in the salty water.
Okay, so it's grabbing the lithium and doing something with the chloride.
Exactly. This concentrates the lithium.
Wow.
Then in the second step, they reverse the electrochemical conditions.
Okay.
This makes the lambda MnO2 electrode release the lithium into a separate solution.
And now that solution has a much higher concentration of lithium.
Right, that's the key. The researchers who developed this method reported 56% lithium purity after the first cycle and 99% after the second.
That's impressive. 99% is almost pure lithium.
Yeah.
So what about the practical aspects? How long does this whole process take?
Each cycle, capturing and releasing, takes about 17.4 hours for the capture phase and about 21 minutes for the release.
17.4 hours, that's quite a while.
It is, but the energy consumption is relatively low, about 3.07 kilowatt hours per kilogram of lithium.
That's not too bad.
And that's less than the current market value of lithium.
So economically, the energy cost is manageable?
Yeah. But there's a catch, as always.
What's that?
The biggest cost is the electrodes themselves, especially the silver.
Ah, silver's expensive.
Yeah, while manganese oxide is relatively cheap, silver isn't.
So the lifespan of the silver electrode is really important.
Definitely. It determines the overall cost effectiveness.
Does the system regenerate the electrodes?
The developers say it can, but other research shows that silver chloride electrodes might lose capacity over time.
So more research is needed on the reusability.
Exactly. This method was chosen for further analysis because it's one of the few that has actually shown that it can extract lithium from desalination brine.
That makes sense. They wanted to focus on something that's been proven to work, at least in the lab.
Exactly. And they also considered another method, path 6, which is chemical precipitation.
Chemical precipitation, okay.
This is what they used for extracting magnesium, and they said that if you're extracting multiple elements, you might be able to share some costs.
That's smart, making the whole process more efficient. So for elements that are more abundant in brine, like magnesium, chemical precipitation is a good option.
That's what they found.
Interesting.
Okay, so we've talked about some of the technical challenges. Now let's see how much material we could actually get.
Okay, the potential scale of all this.
They looked at projections for global desalination water demand in 2050.
Okay.
They used the IEP scenario from a 2020 study.
IEP, what's that?
It's a middle ground estimate for future water needs.
Taking into account population growth and water use efficiency.
Exactly. And then they needed data on seawater salinity around the world.
To know how much salt is in the water in different places.
Right. They used data from NOAA, the National Oceanic and Atmospheric Administration.
Okay.
They divided the oceans into 145 regions.
Wow, that's pretty detailed.
It is. And then, using what we know about the composition of seawater, they could estimate element concentrations for each region.
Based on the salinity levels.
Exactly. The saltier the water, the more stuff is dissolved in it.
Makes sense.
Then they had to figure out how much brine would be produced.
Based on the projected desalination water production.
Right. They assumed a 50% recovery ratio for SWRO plants.
Which is typical. We talked about that earlier.
And with all that, they estimated the total global potential.
So what do they find?
Some pretty remarkable numbers.
Oh, yeah.
Table 1 in the paper shows the estimated 2050 potential for the top 15 most concentrated elements in brine.
Give me some examples.
For chlorine, sodium, and magnesium, we're talking tens of thousands of megatons per year.
Tens of thousands. That's huge.
It is. But for some materials, the potential extraction in 2050 wouldn't even be close to what we produce from land-based sources.
So it's not a solution for everything.
Not yet, at least. Figure 2 shows where they expect most of the brine to be produced in 2050.
Okay, which countries?
Places like Pakistan, China, the United States, and Iran.
Those are some major players.
And figure 3 zooms in on the potential for lithium and magnesium.
Okay, tell me about lithium first.
For the IEP scenario in 2050, the theoretical potential for lithium extraction from brine is about 294 kilotons per year.
294 kilotons, assuming 80% extraction efficiency.
Right. For context, global lithium production in 2018 was about 95 kilotons.
So more than 3 times the current production just from brine.
That's what they estimate.
That's significant.
Now for magnesium, it's even bigger.
Okay, how much?
About 2,230 megatons per year could be extracted from brine in 2050.
2230. Wow.
Compared to just 0.9 megatons produced globally in 2018.
That's over 2,000 times the current production.
It's a massive difference. Figure 4 shows the top 15 countries for lithium extraction potential.
Who's at the top?
Pakistan, followed by China, the US, and Iran.
So the same major players we talked about earlier.
Exactly. The paper points out that even these top countries could potentially extract amounts of lithium comparable to or even greater than total global production in 2018.
That's amazing. So each of these countries could become a major lithium producer.
It's possible, and they also have massive potential for magnesium.
We're talking orders of magnitude higher than current production.
Figures 5 and 6 show the projected growth in lithium and magnesium production potential from now to 2050. It's a clear upward trend.
So the potential is only going to increase over time.
That's what the projections suggest. Then Table 2 ranks the top 15 elements by their potential relative to 2018 production.
So which elements stand out?
Magnesium and bromine have incredibly high potential. Lithium is also there, but not as dramatic as magnesium.
What about the other elements?
They suggest that materials with a 2050 extraction potential less than 30% of current production are probably not viable.
So there's a cutoff point. It has to be worth the effort.
Right. Figure 7 looks at how much of our future lithium demand could be met by brine extraction.
So what percentage are we talking about?
They estimate between 27% and 33% depending on different lithium demand scenarios.
27% to 33%? That's a decent chunk.
And it could increase in the second half of the century as desalination grows.
And potentially less demand for newly mined lithium due to recycling.
Right, so there's definitely potential for lithium from brine.
Especially as a way to help meet future demand.
But let's go back to the practical side. What are the challenges in actually getting the lithium out?
Yeah, the techno-economic hurdles.
Table 3 shows the daily lithium and magnesium extraction potential for a plant that processes 1 million cubic meters of water per day.
1 million cubic meters, that's a large plant.
It is, and they looked at different seawater salinity levels.
Okay, so the saltiness of the water matters.
In less salty water, you need to process more to get the same amount of material.
Which could affect the cost.
Exactly. Then they looked at the theoretical capabilities of those electrochemical electrodes.
The ones we talked about for lithium extraction.
Right, they calculated the maximum amount of lithium those electrodes could capture in theory.
But in practice, it's usually lower, right?
Yeah, the actual capacities achieved in experiments are about 20% for lambda MnO2 and around 50% for silver.
20% and 50%, so quite a difference.
With those real-world capacities and the lithium in our example plant, they calculated how many electrodes you'd need.
So how much lithium could that plant produce?
About 99 tons per year, with an estimated electricity consumption of 381 megawatt hours per year.
381 megawatt hours, so about 3.81 megawatt hours per ton of lithium.
Right.
The energy cost seems manageable, but what about the overall cost of extraction?
That's where Table 4 comes in.
What does it show?
It shows the levelized cost of material, or LCOMAT, for lithium extraction.
And the key finding?
Using this electrochemical process, with current technology, it's not economically viable.
Oh, so it's not profitable yet.
Not with current techniques. But they point out that if the electrodes last longer and we can recycle the silver more efficiently, the costs could come down.
So there's hope for the future, but we need those improvements.
Exactly. And the economics are really sensitive to silver recycling efficiency.
Because silver is the expensive part.
They even estimated the potential global silver demand if we extracted all the lithium from brine in 2050 using this method.
So how much silver would we need?
It could be more than the entire global silver production in 2018.
That's a lot of silver.
It raises questions about silver availability and cost.
Even with recycling.
They also looked at magnesium extraction from the same plant.
Okay, what did they find?
The amount of magnesium is so much greater than lithium that co-producing them is challenging economically.
Makes sense. The scales are just too different.
So what are the broader implications of all this?
Yeah, the big picture stuff.
This research shows the potential for getting valuable materials from desalination.
Especially for elements that are present in higher concentrations.
It could improve supply chain security and create more diverse resource sources.
So less reliance on imports, potentially.
But for low concentration materials like lithium, we need better extraction technologies.
To make it economically viable.
Regions with water stress and high salinity could become material extraction hubs.
If those technologies are developed.
They see magnesium extraction as very promising for meeting future demand.
It seems like a no-brainer for magnesium.
Lithium from brine could also help.
To alleviate supply pressures.
But many other materials in brine are not yet viable.
Right. We're still limited by what we can extract economically.
The paper also mentions that researchers are exploring other lithium extraction methods like chemical precipitation.
So there are different approaches being investigated.
And the field of electrochemical methods is evolving rapidly.
New electrode materials, better techniques.
But many studies are still limited by the concentration of the water they use.
So they need to test with more realistic brine concentrations.
Exactly.
What about those advanced technologies like ion-selective membranes and adsorption?
They're being investigated for directly capturing lithium.
Even from seawater?
In some cases, yes.
Is that viable?
There have been some promising lab-scale results.
Okay, so it's early stage, but potentially interesting.
The key seems to be extracting multiple materials at once.
To work towards zero brine discharge.
And cheaper renewable energy is crucial for making this possible.
It all ties together.
The paper mentions a project that achieved very high material concentration in brine after maximizing freshwater recovery.
Wow, so they managed to extract a lot of stuff from the brine.
It's a promising result. They also talk about lithium from geothermal brines.
That's interesting.
It's another source of lithium, and the concentrations are higher than in desalination brine.
So maybe another potential source to tap into.
There are even planned commercial operations in that space.
Wow, so things are moving forward on multiple fronts.
It seems like finding efficient ways to extract these elements from different brines could change how we deal with water scarcity.
And turn it into an opportunity.
So, wrapping up this deep dive into material extraction potential of desalination brines, what's the key takeaway?
Desalination brines have huge potential for critical materials like magnesium and lithium.
By 2050, we could be extracting more of some elements from brine than we currently produce globally.
And lithium from brine could play a crucial role in meeting future demand.
But we have to be realistic about the technical and economic challenges.
Especially for those low concentration elements.
Ongoing research into extraction technologies will be essential
To unlock the full potential of brine.
So here's a final thought. As the world needs more fresh water and materials for a sustainable future, could securing one resource unlock the other?
It's a fascinating idea.
Could desalination become a key part of a circular economy?
Turning waste into a resource.
What innovations will make this happen?
And what will the impact be on global trade and resource independence? It's definitely something to keep an eye on.
It is. It's a whole new way of thinking about resources.
Yeah, a really interesting area for the future.
Absolutely.
Thanks for having me.
Thanks for joining me.